Hi and welcome to the third class of Python scripting in Cinema 4D. This time we're going to look at the MoGraph Python effector, which will let us finally access and modify specific clones in a cloned object group. This will let us generate animations like these here, which are completely parametric and look pretty nice if you ask me. And this is all just one single cloner using a single Python effector. Okay, so in the course of this class we're going to get quite close to this, I think. Even if we don't finish with quite the same results, I will attach the complete scene file with this project to the class so you can play around with it some more and build your own animation based on it. Okay, so let's get started. First of all, let's build a trusty cube. Okay, and a cloner. Let's make this a bit smaller so we can see better. Right. So there we have 3 clones. Okay, so previously it was quite difficult to get to any of these specifically and modify them. You could of course put other effectors on them, like a plane effector or random effector, but you couldn't just say, okay, give me cube number 5, make it, I don't know, 500 centimeters big, and the other one 100 centimeters. So now with the Python effector, we can actually do that. So let's add that. There we go. And right off the bat, you saw something happening. The whole cloner jumped up a bit. That's because the Python effector, just like all the other effectors, has this parameter tab, and also the fall off tab. They work exactly the same as with every other effector, like the plane effector. So I can just move the cubes like this, position, scale, rotation, color mode, all that. So we leave this turned on, and actually let's move it a bit around. Actually, let's make it an even 100 everywhere. Okay, so this is nothing special yet. What's special is this part here. So the effector has 2 modes. There's the parameter control and there's the full control. We will look at both, but we will start with the parameter control. There's already some stuff in here. Let's have a look what's going on there. So let's make this smaller so we can still see what's going on, but we have more space for our source code now. So first of all, of course, it's importing the c4d module as always. And then we are importing the MoGraph module from the c4d modules module. And we are aliasing it by as mo. So what this does is, first of all, this part here imports MoGraph in a way that we don't have to type out c4d.modules.mograph anymore, but we could just type MoGraph. And then we use this as an alias. So where we say mo, that actually means c4d.modules.mograph, which happens in the very first line already. So right here we call the MoGraph module, and then the function ge get mo data op. Op, as you may remember, is the object that the Python script is running on, which means this Python effector here itself. And the Python effector, because it is being used by this cloner object here under the effectors, is passing through the cloner data from this cloner through the effector into that script. So we don't have to get the mo data from the cloner, but we get it from the tag. And this mo data we write into MD. And if there's nothing in there, so let's say that Python effector is not being used by any of the cloners, meaning it's nowhere in the effectors tab here, then it would return none, and then we would return a 1.0. And right off the bat, this should look different to you from what we did before, because normally what we had been returning so far were objects or true and false booleans, whereas here we return a floating point value. Why that is becomes clearer when we look at these 2 lines here. Let's get them apart. So first off, there's the index, and this uses the function get current index, What this does is it will give us the index of the clone within the cloner group that we're currently working on. And then there's the blend ID, which will get you what Cinema already calls the mode. What this gives away right away is that we are working not with the entire cloner object, so not the group of clones, but with every specific clone by itself. And to make this clearer, and we ignore this for a moment, to make this clearer, let's have a look what's actually happening. So we just print out, let's make it a bit nicer. Remember to always put the string function around it to make sure you don't get an error, because as you know, you can't concatenate strings and integers just by that. So you have to convert the integer to a string. And let's print out the mode as well. Okay, let's see what happens. Whoa, a lot of output. So let's see. Index 0, mode 1010. Index 0, mode 1011. 0, 1011, 0, 1011, 0, 1012, 1012, and so on. And you see it's all index 0, and then we get to index 1, and you notice it's the same modes again. And so on. And it's 3 in total, just a number like our clone. And you see it keeps on going because, of course, the tag is being evaluated a number of times. Right, we have 3 indices, so from 0, 1, and 2, and a number of modes. So obviously 0, 1, and 2 stand for the clone 0, 1, and 2. If we had, I can show you, if we had 4 clones, then we had 4 indexes. So always remember they start counting at 0. So now these modes, let's make this smaller so we don't have that much output. So these modes, they stand for, well, these blend IDs. So what that means is that on every frame, this tag will loop through the clones, and for each clone, it will loop through a list of blend IDs, do something to them, and then return a value. Now these blend IDs, what do they stand for? These numbers. Well, they stand for parameters. And let me just show you where you could find them. They are in this directory here. So on a resource modules object res description, and then in the obasefactor.h. So that's the header file. And that's already open in here. And there we have it. These are the numbers you saw earlier. So the 1010 stands for IDMG base effector position, and scale, rotation, and so on. And all the way down. So now I should have become quite a bit clearer what's happening here. Cinema is checking the parameters for every single one of these here. No, sorry, wrong object. So here, these parameters, checking them, and then returning this value. And what this value is a factor by which these parameters are being applied to the object. So that means with 1.0, the entire value that's being set here is being applied to the particular object. And what happens here is that we check whether the current mode is working on a specific parameter, like this one here, IDMG base effector position, like I told you just a second ago, that equals to 110. So this one here is being called like this, and this evaluates to 110 internally. Always remember to put the c4d in front, the namespace, otherwise it won't be found. And so that says if the mode is currently looking at the position parameters, don't return 1.0, return, well, a vector of 0.5. Now remember when we created a vector earlier, we always put in 3 values. There's another way to create a vector is by creating it with a single value, which means that for all 3 values, that single value will be used. So this is exactly the same as if I were to create the vector like this. Sorry. So that's the same. And what this does is it returns an x, y, and z value for the position like this, which is then multiplied with whatever is in here, and then it's applied to that cube. So let me show you actually. So we have 100 everywhere, and currently, oh, let me turn off the printouts because it's really slowing down Cinema. Okay, so now we're good. So currently, these two cubes are, well, they're here. So, and according to this now, they should be 50 away. So they have 1/2 of 100. If I were to change the x to 1.5, there we go. See, now you can see, if you look at the grids there, this actually has moved not by 100, but by 150. Oopsie. Actually, the easiest way to show you. You see? 150. Okay, so basically that's all there is to this Python parameter mode, Python effector parameter mode. What you do is you loop through each clone, then you then modify its parameters, or it's the factor of each parameter, and then you return that. And that can give you some interesting results. Of course, we can modify all of these, and let's see. And this would be scale, most likely. Yes. And well, let's leave the same parameters. What just happened here? Where have they gone? Let's see. Well, they're all overlapping, I think. So, oh no, you know what? Let's do something else. Let's also check for the index. So, actually, let's use the index to modify these vectors, because you can multiply a vector with a single integer, and index is a single integer. So we just multiply it with the index, and there we go. So now we get some different results. So we have one here. Oh, yeah, of course we only have 2 clones, that's why. So let's make a few more. And there you have it. So this is somewhat similar to a step effector. But of course you could put in some intricate formulas in here and make it much more interesting. Like we could we could use our trusty syncosp module or function from the utils module. So import c4d utils, and then well, definitely some interesting results. So yeah, that is something to play around with, really. I don't want to go too deep into this because personally I barely ever use the parameter mode. What's far more interesting is the full control mode. Still though, this can be really cool if you want to have a preset value in here, in here, and then just gradually modify it for each clone. Or you can build your own random effector this way as well. And you don't have to build your user data interface, you can just use these parameters, and it's quite straightforward, really. Right, But let's go to what I really wanted to show you, which is the full control effector, and which is also what we're going to use to make that scene that I showed you in the beginning. Let's start like before with a simple setup, a cube, a cloner, and the effector. There we go. Once again, we'll make the clone smaller so we see what's going on, and this time I turn off all the offsets in the cloner and also in the effector. So now we have 3 clones, or actually let's make it 10, all on top of each other, so they're all at the same position. Okay, and let's see, switch this over to full control, and whoop, something has happened. Once again it has moved, but if you remember, I have turned off the parameters, and you see the parameter tab is actually gone. So where is this shift coming from? Let's see. Make this a bit bigger again. Well, right off the bat we see a 100 here. So could that be where our shift is coming from? Well, we'll see. Let's go from the top again. Well, we're importing the c4d module again, and the same as before, the MoGraph module. And we get the Mo data, just like before. But then it becomes a bit different. First of all, we don't get an index anymore, because contrary to what the parameter version did, this one is not looping continuously through the clones. This one instead will give us an array of clone data, and that way we can specifically pick out data from that array and put it back in, and thus modify specific clones without looping through the entire thing every time. Right, so like I said, this gets the count. So in our case it would return a 10, which we can check, of course. There we go, 10, that's the number of our clones. And then it returns an array of Mo data matrix. Now what this exactly does, we will look at later, but for now let's see how many entries that has. So let's look at the length of that array that was returned. And again 10. So that means the number of clones and the number of entries in that array are the same, meaning that for each clone you get an entry in that array. And then also different to before, we now get the fall-offs, and these are the fall-offs from this tab here. And it's just like with all the other fall-offs you deal with in effectors, you can switch between spherical and so on. And these, basically what the fall-offs do is, let's take, for example, a spherical fall-off. What this does is, in the center, the value that's being returned when it's checking for the fall-off will be 100%. And then to the outside, it's getting less and less and less. And, well, depending on your settings, it goes to 0 then. And that is exactly what these fall-offs carry. So with that fall-off, we can calculate, relative to the position of a clone, how much the effector is going to affect that clone. Let's leave it as infinite for now, so it's not interfering, but we will test it out later. Right, next step. We are going to loop through the entire array and modify it. Now, why have they reversed it here? Well, I don't know, to be honest. I think it works either way. There's really no specific reason. Reversed, basically what it does is it just takes a list and flips it. So yeah, we'll just leave it as it is, but you could just as well not reverse it. So, okay, and in this case we're not doing a for each loop, but we are counting through the amount of entries in the array. So why are we doing this? Because to access the array, we have to pass in an index, which is a numerical, an integer. And if we were to loop through the array itself, we wouldn't get that value. We wouldn't get the position of whatever is being returned in that array. Let me give you an example. So this array has 10 entries, meaning there are 10, well, of whatever it is in here. We haven't looked at that. So there are 10 objects in that array. Now, if we were to use a for, let's say, for m in mr, and m, let's see, and you see we get 10 matrix objects in there. And if we wanted to change these now in that array, it's actually an easy mistake to make. But let's say we wanted to change that, and we were to go ahead and say m equals whatever, it doesn't matter. So let's say we wanted to change that matrix and we want to put it into M, and we loop through it like this now. What happens is that while we are in the loop, this variable M will hold the changed matrix object. But once we leave that loop, and once we go to the next M, that M will be changed again to the next loop. But this is not the M that's in the array. This is just the M that's in this loop. Meaning that once we leave this loop and we look at the array, none of it will have changed. Let me just show this to you in a very simple example, because this is quite essential to know. Let's make a very simple list, L, and make it 0, 1, 2, and 3. And now we are looping through that list, and this should now return 1 to 3, 0, 1 to 3. Of course, we have to tell it to print. There we go. Now, if I were to go ahead and change this now and say I should be, well, I plus 10, for example. And now I'm printing I. Okay, so this looks good, doesn't it? And now let's print the same thing. Oops, sorry. Print L and see what's in that array. And there you see, while we have changed the value within the loop, we haven't changed it in the array. So the array is still 1, 2, 3, 1, 2, 3. While in here we added 10. So this won't work, and this is the same if you were to deal with a list of objects, be it a matrix object or be it base objects, cubes, whatever. If you change them this way around, then you will end up with, well, unexpected results, because all the changes will be lost once you leave that for loop. So what you have to do instead, and again, let me show you using that same example. So instead of looping through the list, we will loop through a range with the length of that list. Now this is a bit hard to see. This is still the character L. This is not a 1. So what that means is we are looping, and the length of L is 4, of course, because it's 4 entries. So we're looping from 0 to 4, 4 not included, meaning that this here will return 0, 1, 2, 3. Perfect for our purposes. So once again, we have the old value, and instead of adding to the object directly, we are accessing the array, which was L in our case, and we're using the index of I, which is again 0, 1, 2, 3, and change it to okay, and again we're going to print L. Let's do that here. Execute this. Whoops, what has happened? Line 23, what have I done? Ah yeah, well, it should be L, not I. There we go. So this was the old example where we changed it and it didn't change the array. This is a new one where it did actually change. And of course I was printing I here, so it doesn't make any sense at all. But, well, I think you get the idea. So instead of changing the temporary object that we create within the loop, we change the array at the index of I, and then we end up with an array with the correct values. Okay, so that's just a short excursion into Python. Let's get rid of all of that. And to make a long story short, this is why we are doing it this way. So we're looping through the length of that array, which is also the count. So we could have just as well used the length of that array, but the count will return the same value. And we're looping through that, and we are accessing that array directly through its index and then modifying it. Now, unfortunately, it's time for another excursion before we get into this, because to modify the position of these objects, we can't just go ahead like before and say set position, set position relative, absolute, set rotation, this kind of stuff. No, unfortunately, we have to change the object's matrix. And the matrix is where the absolute global position of each object is stored. And not just the position, but also the scale and rotation. And to understand what the matrix is, it's best to have a look at the documentation again. There's an interesting part about matrices in the, I think it's the utils. No, actually, let me just check. Just go through the matrix entry. And at the bottom of that entry, there's a nice introduction about what the matrix is all about and how it works within Cinema. As a short summary, a matrix object has 4 vectors, 3 of which specify the scale and rotation, and 1 specifies the position. The vector 1, 2, 3 are there for the rotation and scale, and off, meaning offset, is the position. And to show you a bit clearly what it is, the best idea to think of, the best way to picture the matrix is to think of these 3 arrows here. Think of them as the 3 vectors that we have, v1, 2, and 3. And as you see, they point in different directions, and they are each of the same length. And that's what happens when you have an object with a matrix that's like this one here. And once you start, let me just go and actually let me just make a new scene. Right. So there we have our object. So basically think of these arrows as its matrix. And when I turn that object, you see that these are now turned. And the matrix will store the rotation or the vector of these 3, which then becomes the rotation. And when I scale that object, now unfortunately that's not being shown here, when I scale that object and make it bigger, this vector here, like if I scale it on the y-axis, this one here becomes longer, basically. So they're all based on 1.0, so 1.0 being its default scale. And when I make it longer, it just becomes 2.0, 3.0, whatever. So that's how the first 3 vectors work in that matrix. And the 4th one is where I store the position in space. Okay, sorry, that's just a really quick introduction, and it's a big topic. And I suggest you have a look at the manual again. Like I told you, the easiest way to get there is through the documentation, through utils, then select any of these matrix functions, which we will look at in a second, and select the matrix type, and then you end up at the documentation for the matrix object. And at the bottom, there's a link actually. At the bottom, you will see this article, and it explains what the matrix does, and it even gives you some examples. So that's a good read. You should definitely do that. Right. Anyway, let's go back to our example. Okay. So this one here, this one returns an array, and we saw it returns matrix objects. However, this is not all it can return. So once again, back to the documentation, back to start, and modules, MoGraph. and modata. So if you remember, we get the modata object first, and in there we have the getArray function, a couple of getArray functions here, but the important ones being the getArray, the setArray, and also the getBlendID, falloffs, and so on. These are all part of the modata object. But let's click on the getArray one. And you see here, where we got the modata matrix, you can get all kinds of arrays here. So we get the color one, we can get the size, we get the UVW tags, data, and weight of the clones, this kind of stuff. So the one you will probably use the most is the matrix, but there are a couple other interesting ones here, like the color one. Don't be confused by this one here. This one looks like it returns the scale of your object, and you will play around with it, and you will notice that nothing happens at all. And that's because this is not the scale. The scale is actually still in the matrix. This is just being used exclusively by the matrix object. So that's the matrix object here. That's the only one that's using that value. All the others are not. So yeah, don't use that one with the cloner. Just use the matrix one. And for now, we will stick to the matrix one. And as you see here, the return types are of type matrix. So this is returning an array of type matrix, not just matrix itself. Okay, so like we saw before, we have 10 matrices here already. Let's do something with them. So the default setting here is to pick the matrix of the current of one of the clones that we're looping through. Then pick that matrix's offset value, so that's the vector that's setting the position, and add to that the fall off data, which we get here, times 100.0. 100.0 being a unit of length, in our case 100 centimeters here. And you have to think of this one, because think of the order of calculation here, dot before plus. You have to think of this one being surrounded by brackets. So first, before we add to the offset, we multiply our value with the fall off. So like I told you, when you have a spherical offset to the outside, once we get to the outside of that sphere, that fall off will move towards 0, and well, our effect will be lowered by the same amount. All right, so this of course is not doing a whole lot, because it's all moving all the objects by the same value. Once we have modified these arrays here, and this one is correctly modifying the original array, we have to remember to put the array back into that object, because otherwise the changes won't be applied. So to do that, we use the set array. We pass it the same parameter that we used here to get it. We pass it the array itself, and we pass it another one, a Boolean parameter, that is doing, where is it? Not a whole lot. It's just telling us whether to use the fall off or not. And in our case, well, yes, we have the fall off. So, and that is it really. And we just return true, because that just means the function is finished. Unlike before, we returned the floating point value. All right, so let's make this a bit more interesting. As usual, we will first of all get the current frame. Right, that's always useful, because this means we can use that for animation. And then I think once more we will get the util class, and we will use the current frame, I think, once again together with our trusty syncos function. And we turn it into radians again. And again, you notice me using this sine and cosine all the time. It's a very easy way to get stuff moving because they change all the time over time. Obviously, you can use anything you want here to modify the position. So anyway, we have some values here, and why not multiply this times sine, and also multiply it times the index of the object, so we get different position. And well, nothing much changes because we have an error. Why do we have an error? See where? Oh yeah, because I forgot an S. Let's try this again. Oh, this looks better. And immediately you see each clone moving around. Okay, but this is not very exciting. Well, it is a bit exciting, but not really very exciting. Now let's change the scale. If you remember, previously we would just set scales by using the function set absolute scale, set relative scale, set absolute position, all that. I told you we can't do that here because we have to work with matrices. And to change the matrix value, you can't just, well, you could theoretically go and calculate the position of these three vectors yourself, but it's a real pain to do that. What you do instead is you use some of the util classes that we have here, and that's in utils again. And you can see here there's a number of them. We have matrix move, we have matrix scale, rotation on each axis, and some other functions that we won't use right now. The interesting one right now is scale and the rotation ones as well. For now, the scale. The scale, just like all the other ones, like the set absolute scale function, will require a vector as a parameter, and it will create a modification matrix. So it's not actually changing your matrix. It will give you a matrix that you can then multiply with the original matrix to get what you want. Okay, that sounds more difficult than it actually is. Let's just create a matrix for us. So our scale matrix we'll call let's call it matrix scale. And it's in c4d utils dot, what was it again? Yeah, matrix scale, of course, yeah. Matrix scale, and we want to scale our, well, let's see, how do we want to scale them? Let's scale them differently. So let's scale them based on their position in that array. So let's scale them, well, we have 10 of them, they go from 0 to 10, so let's scale them I divided by 10. So this means now this will be 0, 1, 0, 0.1, 0.2, and so on until 0.9. And our vector will be created with x, y, and z using that same value. And that vector will then be fed into the matrix scale function and will return a modification matrix that we can then apply to the original matrix, which is this one here. So what we do is we use MRI, and it has to be applied to the entire thing, and equals, and there's actually a shorthand, so we could of course type MR like this, and then times matrix scale. But you can also, instead of this part here, just type times equals matrix scale. So that means this is just a shorthand, and it will take this one here, this value here, and multiply it with whatever is on the right hand side. So I can have several things on the right hand side, and it will just multiply it with this one here and write it back into itself. And this should result now in a slightly different result. Let's see. Compile it, execute it. There you go. You can see these are now scaled differently. And to make it even more interesting, you could now go ahead and multiply that with Oh, I don't know, sine times y again as well. Let's see what happens. Okay. Let's use cos instead. This is more interesting. Okay. Okay, so these kind of loops, they can be used for all kinds of interesting things, because let's say we have a cloner of not 10 but 100 steps. Whoa, that's a bit, well, it's getting massive. That's because of our scale here. Let's turn that off for a moment. So now we have plenty of them. And of course, it's a bit boring to just watch 100 of these cubes all in a row. So what you can do now is, thanks to this looping through the number of objects, you could go and use things like modulo and division to build columns kind of your cubes. So basically you have to think of the cloner now just as a, well, just as an object generator. It's not so much taking care of the positions anymore. It's just spitting out objects for you at a specific number, and you can position them in whatever way you like. Let's just hop over, because we're running a bit out of time, hop over to that example I showed you earlier, which is this one here. This is based on exactly what I just showed you. It's just using some calculations that are a bit more than just the sine and cosine. Let's have a quick look here. So it's the same as before. I've just been using some user data fields here to modify some things, and I will document this for you in detail. What I then do is I use, like I told you, I use modulo to make columns of these objects, and I'm also using the fall off. Like I showed you before, that's just being applied down here at the final positioning. And this one I have keyframed in my case, and you can see here now the fall off has a direct effect on the script as well. You can combine all these parameters. That's a great thing. It's not just that you're setting the position and rotation and whatever through the Python script. You can combine all the other effectors. You can throw other effectors in the mix as well, of course. You can, I don't know, you can change the strength through this parameter. There's so many parameters that will all add together to give this effect that you want. And yeah, well, I have added some scaling as well. That's got to do with the column that I spoke of. So basically, one of these snakes is one of the columns of objects that I created. Then I go and scale it down to the end, and the next column will scale from one again back down, and so on. It's really quite a lot to show, and I hope a well-documented source code will help you to understand what I did here. I've also used a couple other classes, like the usual random class that we used in previous classes. And yeah, it all comes together at some point and gives you this animation. And I have to admit, quite a number of these calculations have been set up by trial and error. So it's not like I just pulled them out of the air. And that's a great thing with Python compared to another language where you would have to compile these. You can just dive in and just change values on the fly and see what happens. Use these user data sliders to get all kinds of weird and wonderful effects. And yeah, I suggest you just start and play around. And well, I'm really looking forward to see what you come up with. And if you have any questions, which no doubt you will have, just let me know. Ask me in the forums, ask me personally. But of course, the forums are always better. Yeah, well, next week we're going to have a look at how to collect scene-related data and pass it on to you, for example, your render farm or other applications. How to write data to files, this kind of stuff. I hope that sounds interesting to you, and yeah, see you next week. Bye.